Here we are looking at a cantilever beam that's fixed at one end and you have a force applied at the other end. It's one of the simplest problems in solid mechanics. And there are different ways you can model this, and we will look at one particular approach. But before that, I wanted to talk about the at least 3 different ways you can model a cantilever beam. So I'm going back to the what's under the black box framework. And the physical problem we have is a beam. And this is not to scale, it's just a schematic. And we fix the beam at one end and we apply a force at the other end. Now, one way to model, the mathematical model that you can build for the beam is based on what's called 3D elasticity, which some of you might have seen. And here you solve the equilibrium equations, which are differential equations, in a domain that is defined by the geometry of the beam, the 3D geometry of the beam. Okay? So your physical problem is always 3D and your mathematical model is 3D. Another approach that is related to this is you say, hey, I'll make an additional assumption and that there are no variations in the strains and stresses in this direction. And you can then reduce this to 2D elasticity, particularly plane stress. And in this case, you can, you need to solve the differential equations in a domain defined by a rectangle that could correspond to the front face of the beam. So your physical problem is 3D, but now your mathematical model is 2D. And it'll solve faster than the 3D elasticity, but it's got more assumptions in there. The third approach is different from elasticity. It's, you can use what's called engineering beam theory or Euler-Bernoulli beam theory. And this is a very different approach from elasticity. And let me talk about what you do there. What you assume is that you need to determine how only the midline deforms. So this is the midline, or it's also called the neutral axis. And you make some additional assumptions that we'll look at soon, so that once you know how the midline deforms, you can back out how the entire beam deforms. Which means that in Euler-Bernoulli beam theory, you need to determine only the deformed state of the midline. And since you're solving things along a line, you can think of this as a 1D mathematical model. And you might have seen this in introductory statics. And the mathematics is more tractable, but this is most abstract. The 1D is most abstract. So you can use all 3 approaches in ANSYS, and it's actually instructive to do that. And we get students at Cornell in the finite element course to do that. Over here, we are going to focus on the 1D, Euler-Bernoulli beam theory approach.